Hello everyone, we are about to talk about how to synthesize amino acids, and I'm going to show you three different ways of arriving at the same outcome in essence. Um, One of the ways to go about synthesizing amino acids in the laboratory is to employ a reaction that we've talked about in the past called the Hell-Volhard-Zelinsky reaction. And to refresh your memory, this reaction is simply taking advantage of enolate or enol chemistry to be most exact. Um, in short, you take a carboxylic acid, you turn that into an acyl chloride with thionyl chloride, you expose that to bromine, elemental bromine, which brominates the alpha position, and at that point you quench the reaction with water to end up with the monobrominated carboxylic acid. That molecule can then be treated with excess amine to undergo an SN2 reaction that displaces the bromides for an amine group. And at that point, you have yourself an amino acid. So as you can see, the original carboxylic acids in the series has to have the side chain of the amino acid present at the very, very beginning. And your carbon, your alpha carbon, has to have CH bonds. If it doesn't, then you can't really do this type of reaction. But for the majority of the amino acids that we care to talk about in this class, this does the trick. So to refresh your memory, we're going to go through the entire mechanism just so that we are sure that we're dealing with basically talking about being in the same page. That's what I'm trying to say right here. So the exposure of your carboxylic acid to thionyl chlorides allows you to bind to thionyl chlorides, produce the complex shown here. The sulfur oxygen double bond is reestablished, kicking off chlorides, and the chloride can remove that proton. It can reshuffle it so it goes onto your carbonyl oxygen, and the chloride can then attack that activated carbonyl to basically give you the tetrahedral intermediate shown in here, now with the chloride present. Now, you may recall that the leftover thionyl chloride reagent that's still bound to that carbon can act as a good leaving group, because when this oxygen allows its lone pair to come back down and recreate the double bond, the carbon-oxygen bond right here will be broken, and it will basically come all the way around to bind to sulfur, and that will also kick away the chloro that you have in that molecule. So the end result is that you will produce sulfur dioxide. You will have chloride left over. You also have protonated acyl chloride. So the protonation, or the proton rather, can be dealt with by directly protonation of that OH bond, or alternatively, you can deprotonate the alpha position, which will move this set of electrons onto the carbonyl carbon, and then the electrons of that pi bond will move over to the oxygen to form the enol derivative. And what you got to remember is that formation of the carbonyl and formation of the enol is really an equilibrium when you have, and it's exacerbated to by the presence of acid, which you're going to get the moment you form or you use thionyl chloride. You're going to be forming HCl, so you'll have this equilibrium happening through and through. But once the enol derivative is formed, having bromine added to your mixture will allow the enol to react with bromine by recreating the double bond, having the pi bond of the alkene attack your bromine, break that bromine-bromine single bond, and as in essence brominate the alpha position, right? So the last event here is that you deprotonate the carbonyl, leaving you with your neutral acyl chloride, monobrominated acyl chloride molecule. So here the last event is that now you quench the reaction with water. So you add water to the mixture, water attacks your carbonyl, breaking that double bond momentarily, leading to the tetrahedral complex shown here. Then you have proton transfer onto that oxo group. And lastly, you have reformation of that carbon-oxygen double bond, kicking away the chloride away from this molecule. The last event is, of course, the protonation of the carbonyl to yield the neutral carboxylic acid, right? So that's the whole scheme that we talked about previously when dealing with enolate chemistry and enol chemistry. So then the last event of the synthesis is just introducing your carboxylic acid to excess amine. And yes, some of that amine is going to react with the OH bond of the carboxylic acid. And that's why you have to use excess to ensure that you have free amine to attack the carbon side right here to undergo the SN2 reaction that leads to formation of your um, amino acid. Okay, so yes, this thing that I'm drawing right here, here it will definitely happen to a higher extent because the presence of the amine group, or technically the ammonium group, serves as an electron withdrawing effect to the carboxylic acid. So now this is even more acidic than it was before. And if you are unsure about that, take a look back at the pKs of the side chain of glutamic acid and aspartic acid. Those carboxylic acids are farther away from the ammonium group than this carboxylic acid is, and so they have lower acidity trends, they have higher pK values. All right, anyway, this will allow you to get to your final amino acid residue. So this is one way to tackle the synthesis of your amino acids, and this is the full mechanism. A second way to accomplish the same task is to utilize this reagent known as amidomalonate, which looks pretty much like this, right? You have the malonate component here on the left side of the molecule, and then here is your amido component that's bound to the alpha carbon of your malonate molecule. This molecule can basically be deprotonated because you still have a pretty acidic proton at the alpha position. So you could deprotonate it using sodium methoxide, the same alkoxy that you have on your malonate molecule. You can then introduce an alkyl halide to undergo an SN2 reaction. So this one is an alkyl halide that happens to have a silyl ether component, and that's because we're protecting this oxygen. We don't want to keep it as an alcohol necessarily because it can get involved in the acid-base chemistry. All right, so by doing those two steps, what's going to happen is that we're going to deprotonate the central atom and we will undergo a substitution event to introduce the methyl oxy trimethylsilyl component. And then after that, we simply react this entire thing with acid and heating, reflux in essence, to ultimately kick out the alkoxy groups of the esters, kick out the acetyl group of the amine, remove your potentially your TMS group as well, and then this will lead to the presence of two carboxylic acids next to each other, which is basically a decarboxylation. So you have a lot of things happening here. And then if it is the case that the trimethylsilyl group did not come off right at this point, then you can force it to come off by adding a simple reagent, a tetraalkyl ammonium fluoride reagent will do the trick. The fluoride's a much better um, element to bind to silicon, even more so than oxygen. So this is a reaction that will happen all due to thermodynamic reasons. And that will automatically remove the trimethylsilyl group if the event of hydronium, hydrolysis didn't do the trick. So I'm going to show you the entire mechanism from beginning to end, if for anything to remind you, refresh you about your carboxylic acid chemistry, right? So as I mentioned before, you have an acidic proton right here. But one thing I want to show you initially is that I want to show you how you make that amidomalonate reagent in the first place, because this is the first time we're introducing it, so it seems a little bit off to just introduce it and have no say about as to where it's coming from. So if you think about your typical malonate chemistry, you could do deprotonations with the same alkoxy group as is present on your ester, and that'll produce the corresponding enolate, right? So remove that proton, the electrons move over here to create enolate. And what you can then do is react this with an equivalent of Br2. So you basically will wait until this reaction goes to completion, which it had to go to completion because the pK down here is down to 9. Your alcohol has a pK of 16, so yeah, this reaction is meant to happen all the way through. So once that's done, you bring in Br2. You will reform your carbonyl, attack with a pi bond onto bromine, break apart that Br-Br bond, and you will brominate the position at the alpha carbon. Okay, so now, right at this point, you will want to introduce your amine, right? So you can introduce amine, do an SN2 reaction literally there, and that will replace that bromine. And one thing I want to highlight is that yes, the amine is a nucleophile, right? But you're not going to have a constructive, or rather a favorable conversion of an ester into an amide. That reaction is not that favorable. So the reaction to do this into the actual SN2 path is a lot more favor than replacing an ethoxy group with your amine group. So this reaction here is actually not too bad. Obviously you don't want to overheat this because that will kind of create problems. But aside from that, this is technically okay. So in the presence of excess amine, you will deprotonate the molecule to end up making the neutral species. And once that happens, you can treat this molecule with acetal, or technically acyl chloride, so that you attack that carbonyl, break the carbonyl bond, have the tetrahedral intermediate shown here, which will have its electrons come back down, kicking away the chloride. And finally, the chloride will simply remove the protons from that NH bond to give you the neutral amido-malonate reagent. So this is one way in which you will make this thing. So once you make it, well, now you can use it to make amino acids, because you could take, once again, that ethoxide base to deprotonate. You form your enolate. Right now I'm skipping it as the carbanion version, but it's an enolate. And then you bring in your SN2 substrate, by which you undergo an SN2 reaction, kick away your chloro leaving group, and now you have that group installed into your molecule. All right, so now we introduce hydronium and we start heating up this reaction. So we're going to protonate all the carbonyl groups that you see here. So we're gonna do it one by one. So we're gonna start with the amide. Protonate this. Now you're gonna have water. The water is gonna come in. The electrons are gonna be kicked off to the oxonium oxygen. Okay. And then you're going to have a proton shuffle event, which here I'm just going to show the proton exchange directly from from oxygen to nitrogen. So we'll have the attack from nitrogen over here, taking up that proton. The electrons go back to oxygen. And now that that nitrogen is protonated, it serves as a good leaving group to our gem diol that we have over here. So the electron pair of that oxygen will come back down to form a double bond, and then the carbon-nitrogen bond will be broken to liberate the amine. That amine can then serve as the base for proton removal of the carboxylic acid that we've generated as a byproduct. So that will generate ultimately, yes, as you saw, carboxylic acid, but more importantly, your ammonium counterpart. All right, now this continues. You still have plenty of acid around, so the acid is going to then go after one of the esters. The carbonyl is going to get protonated. You're going to produce water. Water will then attack that activated carbonyl, breaking that pi bond and forming the tetrahedral intermediate shown right here. At that point, you will also do a proton transfer from the water onto the ethoxy. And once that ethoxy is protonated, the lone pairs of your oxygen will simply come back down to reform the carbonyl and kick away your ethanol leaving group. All right, so that will convert that group into carboxylic acid. So now we're going to do it again. And this time, just to save a little bit of time, I'm going to say you're going to do the same exact mechanism for the other ester, which will get you to another carboxylic acid. And because you're doing this under reflux conditions, the moment you form these two carboxylic acids, they're in prime position to undergo decarboxylation. And that's exactly what's going to happen right now. The carbonyl oxygen over here will attack and remove the proton from the neighboring carboxylic acid, those electrons will move over to the neighboring oxygen while breaking the carbon-carbon bond connection of this molecule. In essence, you'll form CO2 in that event, right? But then this pi bond will also move to the oxygen, and the end result is going to be that you will form an enol of that molecule, and you will also kick away CO2 in the process. So now that you have that, and because this is done in acidic conditions, you will have hydronium simply help you out to turn this back into a carbonyl. So the electrons of that oxygen will come back down. The pi electrons of the alkene will go over to the hydronium to remove a proton. This will produce water in the process, and that water will simply remove the protonated component of your carboxylic acid. Okay. And at this point, we are almost done with the task, because all that will be left to do is remove your TMS group by introducing fluoride in the form of tetramethyl ammonium fluoride. So that fluoride will simply attack the silicon in an SN2 fashion. You will liberate the silicon-oxygen bond, and being that this is done in aqueous solution, you will simply protonate your alkoxy group with a water molecule, and you will produce tetramethyl ammonium hydroxide as a byproduct. But this will generate your final amino acids, right? All right, so that's the second way of making amino acids. I'm going to show you one more called the Strecker synthesis. And here's a good old Strecker. What he basically did is he said, okay, well, we know that we can take aldehydes and we can turn them into an imine by treatment with, ammonia under slightly acidic conditions. That imine can then be treated with a good nucleophile like cyanide to produce an amino cyano derivative. And the cyano group, which is technically nitrile, can then be treated with acids to turn that into carboxylic acid. So that's another way to get around the idea of making carboxylic acids. So I'm going to show you the mechanism as well, just to kind of make sure that we are on the same page about this whole thing. So you will protonate your aldehydes under acidic conditions. You will then have your ammonia base and nucleophile attacking your carbonyl carbon, kicking the electrons onto oxygen. At that point, you will have a proton transfer to the oxygen, so that now you have an amino alcohol, well, a protonated amino alcohol. The amine group will then have its electron pairs come down to form an imine or an iminium ion while kicking away the water leaving group that we have in here. So this will lead to formation of that iminium. And then the iminium, in the presence of cyanide, will simply have cyanide attacking as a nucleophile. The electrons will go back to nitrogen. And now you have an amino nitrile. And here's where the acid will be introduced. So you will then add acid and reflux this solution so that you, yes, you protonate the amine, so you'll produce the ammonium derivative of this thing. But then at that point, you will actually end up protonating the nitrile as well. And the protonation of the nitrile will then start a sequence of events, because now we have also water as a byproduct, which now sees this carbonyl as being activated. So it attacks that carbonyl carbon, and the 1 pi set of electrons moves over to the nitrogen. So now we have that protonated amino imine. So what we'll have now is simply a proton transfer from the oxygen to the nitrogen. And then what takes place now is that we simply, do a little bit of electron movement, right? So bring the electrons from oxygen down, kick the electrons back to nitrogen, all right? And we'll have water coming in. Okay, kicking the pi bond back to the oxygen, but now forming two oxygen hydrogen containing moieties, right? So we'll have this extra proton from the water that just came in transfer over to nitrogen. And right at this point, we have formed a good leaving group. So the oxygen lone pairs will come back down, kicking away ammonia, yielding protonated carboxylic acid. And so the ammonia you generated will simply take away that proton, and it will form your final amino acid. So I just want to make sure that you guys know and remember your mechanisms from the aldehyde chapters, the carboxylic acid chapters, because it plays a big role here, and it hasn't gone away. But being that the video is already long enough, I'm gonna end it right here, and we're gonna pick up next time on oligopeptides. So catch you in the next video. Bye bye.